Okay, so we'll begin. As I said, this is basically a bit of a review of grade 10. The first 2 or 3 days are sort of a review of grade 10 just to make sure that everyone's sort of on the right page kind of thing, and we'll go from there. We got some definitions. Yesterday you got that sort of outline of the unit, and you can follow along that a little bit to see how much we've covered. Some are obviously going to take longer than others. So let's begin. Motion. This is really what people think about when they think of physics, right? You guys probably had no idea when you walked in the door you'd be dealing with protractors and vectors, right? Probably a completely foreign world to you. This is sort of the stuff that people think about when they really think about physics. So, study of motion. Motion of objects, baseballs, automobiles, joggers, even the sun and the moon is an obvious part of everyday life. Motion was undoubtedly the first aspect of the physical world to be thoroughly studied, and this study can be traced back to the ancient civilizations of Asia Minor. Asia Minor is your Greece, your Turkey, your Persia, modern day Middle East, Iran, Iraq, that area. Although the ancients acquired significant insight into motion, it was not until comparatively recently, in the 16th and 17th centuries, that our modern understanding of motion was established. Many contributed to this understanding, but as we shall soon see, two Galileos, that you probably have already heard their names, stand out above the rest, and they are Galileo Galilei, the guy that's got the funny two names, and Isaac Newton. Oddly enough, Newton was born the year that Galileo died, and for some reason we call Galileo by his first name. Much like Beyonce, I guess. Come on, you guys, give me something, no? Right. The study of the motion of objects and the related concepts of force and energy forms the field called mechanics. Notice it's in bold. Do you remember it from yesterday's little things you got to know? Where's my highlighter? I can't find it. I'll use this. Mechanics. Mechanics is the study of motion. And it's customarily divided into two parts. Kinematics, also in bold, which is the description of how objects move, which is what we'll be dealing with for the next 3 weeks. And dynamics, which deals with why objects move as they do, and we'll be dealing with that in the following 2 or 3 weeks. So mechanics is broken down into kinematics and dynamics, and that's the forces one. We start by discussing objects that move without rotating. Not start, we will not go beyond rotating objects. Rotating objects are hard. Like when I throw a tennis ball, right, and I put a curve on it, it's going to go like this. That's hard motion to understand. Okay? We're going to be dealing with straight line motion, and this is called translational. In math, you talk about translations, right? Like over the x-axis and all that mumbo-jumbo stuff, right? Okay, so that's what we're talking about. We're talking about one object moving from one place to another without rotating or anything like that. In grade 12, we do deal with two-dimensional motion projectiles. Okay, that's what it says right here. Okay, speed and velocity. Now, this was on that last test. You guys should know this already, but as another review here, speed and velocity are words often used interchangeably. In physics, we make the distinction between them. For now, we're going to discuss only speed, which refers to how far an object travels in a given time interval. If a car travels 240 kilometers in 3 hours, we say that its average speed was 80. How did I get 80? 240 divided by 3. In general, the average speed of the object is defined as the distance traveled divided by the time it takes to travel that distance, with no consideration for the direction. We don't care. Speed, no direction. How far it goes and how long. You're probably familiar with this tiny little formula right here that I'm going to try to make bigger. I see a few people squinting. Don't be offended if I come up and say, your trip to the optometrist might be in order. It's very blurry. You do have it on your page though, right? Yeah. Yeah, okay. Yeah. Is that better now that it's bigger? So the formula is V bar equals V over T. Everyone's seen that, right? Everyone has seen it. You might not have seen it with the bar over the V though, right? In grade 10, we simplify a little bit and we just say velocity. What does the bar over it mean? It's the standard international symbol for average. Anything with a bar over it means average. If you take first year stats, that's likely going to be the first thing you learn. Okay? V bar, average velocity, distance over time. Where D stands for distance, T is for time, and for this. And I guess that would be V bar for the speed. The bar over the V is the standard symbol meaning average. Okay, go grab a clicker, log in, and let's do this question. Okay, so the first question, how far can a cyclist travel in 4 hours if his average speed is 11.5 kilometers an hour? How far? You're solving for? You're solving for D, right? The distance. Just type in the answer, yeah? Type it in, make sure you hit press enter. Hit press enter, what am I saying? Yeah, just type in the answer. It's got a number pad on it. I know, it's like science fiction. Who would have predicted that 8 years ago? Oh yeah, I had those for years. Do you like using them, Dad? Yeah. You should be able to solve this, grade 10. Megan and Alex left. Okay, let's see how you did. Are you nervous? All right, everyone got it right. How did you get 46? Multiply, right? Multiply. V bar equals D over T. This is 11.5. What is it? 4 hours? Multiply by 4. Okay? I expect you to be able to solve things like that like 15, 20 seconds. Okay? There should be no, you need to be able to solve them. You can't be wondering how to do that now. That should be a given. Okay? If we have to work on it, we will, but you got to be able to do it. Okay, so reference frames and coordinate systems. When you discuss motion, you have to have some sort of reference frame. I already talked about reference lines and vectors, similar concept. When riding in a train, you may observe a bird flying by overhead and remark that it looks as if it's moving at a speed of 20 kilometers per hour. You've probably all done that. Ridden in a train, saw a bird and estimated its velocity, right? Who hasn't done that? Yeah, no. Back in my head. But do you mean it's traveling 20 kilometers per hour with respect to the train or with respect to the ground? What the heck does that mean? Compared to, exactly. Every measurement must be made with respect to a frame of reference. And when you were doing your reference lines on the vectors, Josh and Alex, here's the part where you listen. When you're doing those reference lines, you were setting a frame of reference. I just didn't call it that. I called it a reference line. But you're taking measurements, and some of you unfortunately haven't learned that just yet, that you have to measure from those reference lines. You don't measure, you don't measure between, right? Those, you measure from the reference line. Okay, so that's what I'm talking about here. So every measurement must be made with respect to a frame of reference. For example, while on a train traveling at 9 meters per second, you might notice a person walk past you toward the front of the train at a speed of, say, 2 meters per second. Okay? With respect to the ground, how fast is that person moving? You're sitting there on the train, train's moving along at what, 9? Person walks past you, maybe they're going to the bathroom or something or other, they walk past at 2 meters per second. If I'm not on the train, I'm on the road, how fast do I see that person walking? Don't yell it out, just type it in. How fast does a person on the side of the road see the person walking at? I'm on the train, moving at 9. The person walks past me at 2 meters per second. How fast does the third person on the side of the road, the ground-based observer, see them walking? The first two are on the train. I'm sitting on the train. Dan walks past me. I'm moving at 9 meters per second. Dan walks past me at 2 meters per second. Andy, he's on the side of the road watching us. How fast is Dan walking in Andy's mind? Observant people will notice that the answer's on the page. Does this sound way harder than it really is? Yeah, I certainly made it sound hard, didn't I? It's pretty easy. Punch it in there, Avery. Did you? Oh. It's 11. How did you get 11? 9. Oh, can't write. 9 plus 2. Right? The person that's walking is moving at 9 plus another 2. How fast are you moving right now, Dan? 0? Would you agree?
No. He's not moving.
No? With respect to us, he's just sitting there, right? But say Mr. Smigalski's out on the moon or something or other, and he's watching the Earth spin. How fast does the Earth spin? You'd be surprised at the number. Pretty fast. Right? We're all spinning right now. My head's spinning, right? Our world is spinning like this. Not only are we spinning like this, but we're also going around the sun at a pretty good clip. Like thousands of kilometers an hour. Just keep going. Okay? Your reference frame matters. Okay? This is the person's speed with respect to the train as a frame of reference. It's always important to specify the frame of reference when stating speed. In everyday life, we usually mean with respect to the Earth. Because when I first asked how fast is Dan moving, or we asked to use the rest, we all said use the rest. We didn't say with respect to the Earth. Because you sound weird when you say that all the time. Right? But it really means that. The reference frame should be specified whenever there might be confusion. If you get a speeding ticket, sign says 100 kilometers an hour, right? With respect to the ground, Your Honor, right? I was actually traveling much faster than that, taking into account your spin. You'll probably still have to pay the ticket. It won't work. I tried it. Okay. Boring part. Gentlemen, you need to listen. Really, seriously. Josh, there isn't a question coming now, so you can put that clicker down. Like, I'm not sure what you're doing there. Does it have Space Invaders on it or something or other? I don't know. Flappy Birds or something or other? No? Yeah, you'd all be playing it, yeah, for sure. Okay. Values of other physical quantities also depend on frame of reference. For example, there's no point in telling you that Riding Mountain National Park is 100 kilometers away unless I specify from where. Distances are always measured in some frame of reference. Furthermore, when specifying the motion of an object, it's important to specify not only the speed, but also the direction. And I've got to put a space in there because, man, that's hard to read. I don't know. There we go. For example, if a friend leaves Winnipeg on a jet plane traveling at a speed of 1,000 kilometers an hour, you would like to know what direction this person is going toward. Toronto, Vancouver, or even Ottawa. Often we can specify a direction by using the cardinal points north, east, south, and west, and by up and down. Not always convenient, so in physics we often draw a set of coordinate axes, just like you did in vectors, as shown to represent a frame of reference. And you already know that over here is plus x, and over here on the left is minus x, and up is plus y, and down is minus y. You already know that, right? That is literally a frame of reference. They call that have you guys ever heard of that as a Cartesian set of coordinates? No? Named after the French René Descartes, who first originated it. Objects positioned to the right of the original. Yeah, we don't need to read that. Blah, 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 blah. In 3 dimensions, and they'll deal with this in university, and it will blow your mind, there is x, and there's y, and there's also the third axis, which is z, out at you. Positive out towards you, negative in towards the page. 3-dimensional space, which we all live in. Although most measurements are made in reference frames fixed on the Earth, it's important to recognize that reference frames other than the Earth are perfectly legitimate. For example, scientific measurements are sometimes made on moving ships, in spacecraft, and on the moon. Have you seen Apollo 13? It's a really old movie now. Pretty good, yeah. Pretty good, right? Tom Hanks, Bill Paxton, Kevin Bacon. I think I'm related to him. You remember the magic number? Quite often, a question may list speeds in kilometers per hour. Us nerds use it in meters per second. Remember the rule? Do you remember it? For converting kilometers per hour to meters per second. Kilometers per hour to meters per second. What is the rule? Is it times by 3.6, divide by 3.6, plus 3.6, or times by 1,000? It's okay if you get this one wrong. If you have to guess, just guess. Smelski, you got an answer for us? Well, come on. Did you press enter, Smelski? Come on now, we're waiting on you. Correct answer is B. Right? And as Mr. Smigalski said, what was the number you used? 100? If you're traveling at 100 kilometers an hour down the highway, and you multiply by 3.6, are you telling me you're going 360 meters in a second? Like the length of this table in a second? That's how fast you're going? Oh, sorry, 360 tables in a second. No, you're going 4 football fields in a second? I don't think so. Actually, we all are moving that with respect to the sun, but that's another story, right? Yes, it is divide, right? Divide. You'll need to know that. Can you do it backwards? You better get this one right. You better get this one right. Smelski, you better not be last. Who put C? The rule of Alex is don't listen to Alex. Andrew, tell him, would you please? The opposite, yeah. What was the first one, Braden? You did write it down? You don't have it on your... The first one was times by 3.6, so if you're going the other way, you're going to have to? Are you going to have to start paying attention in here? Yeah, you are. Not just you. Y'all. Okay. I'm going to give you about 6-7 minutes to do those questions to summarize what we just talked about. Go. Oh, are you waiting to the end? Oh. Here's a formal definition for kinematics. It is the description of motion by studying the relationships among the variables of position, velocity, and time. I think you need to fill it in, right? Right at the top there. On the front page, man, where it says kinematics. The description of motion by studying the relationships among the variables of position, velocity, and time. You're going to be hearing those words a lot. It's like listening to Donald Trump and hearing the word China. You're going to hear it over and over again. Can you see those 3 cars? Can you see what color they are? I see you still writing. I'll pause. I'll wait. Kinematics is the description of motion by studying the relationships among the variables position, velocity, time. Okay, let's talk about the 3 cars. They are red, green, blue from top to bottom. Which car is traveling at a constant velocity? It's the blue one? What could we do? What could we do to determine it for sure? What if every second we marked where they were? We sort of left a trail. Would that work if we could do that? Can't quite do it. That would work, right? Okay, well then, okay. Which car has a greater average velocity? Which one has the greater? Do they all start at the same time? They appear to. Which one gets there first? The blue one. So would you say the blue one has the greater average velocity? It's traveling the same distance in a shorter period of time. I would agree. Which car experiences the greatest acceleration? What does that mean? The red one experiences the greatest acceleration? What does that mean, greatest acceleration? Which one speeds up the fastest? Which one speeds up the fastest? The red one. Boom, it's gone. But the blue one, right? The blue one's got a greater top speed, right? It's kind of like driving a dirt bike compared to like a semi, right? The dirt bike, boom, gone. Right? But eventually that semi's going to catch it, overtake, right? Yeah. The green one's just a hunk of junk. Okay. The word motion implies movement from one place to another. Thus, position, where the object is located, is the most fundamental consideration in studying motion. You must understand position before you can understand motion. Do you have to write something in there? I don't know what's up. I don't know. No? You're good? Okay. So the word motion implies movement from one place to another. Position is the most fundamental consideration. In order to specify an object position on a straight line, 3 things are required. You need 3 things to state where a person is. What are they? Oh, they must be on the page. Yes, there must be an origin or frame of reference, some arbitrary starting point. What does the word arbitrary mean? Anyone? What does arbitrary mean? Okay, Brady, stop shaking the floor. Stop shaking the floor. No one else can hear that song. The one that you're listening to in your head. What does arbitrary mean? It means just made up. It means for no reason at all, right? Just wherever we say that's the starting point. So origin or frame of reference, usually we choose some point, call it 0, and that is the starting point or origin, right? On a 2-dimensional axis, we call that the origin. We call that in math, right? If it's a 1-dimensional line, we set some point equal to 0, and we call that origin, right? It doesn't matter where it is on the page. It's arbitrary. It's like nobody cares. Okay? Again, we're talking about the 3 things needed to state an object's position. That's all I'll have. On a position time graph, what do the following represent? A positive slope line means what?
Moving to the right.
Moving to the right. Slope of 0 or flat means? Stopped. Negative slope means moving to the left. You need to know that. Right? That's just like basic knowledge. Gotta know that. Okay, I'm done for the day.